Floating markers appear across the water surface. They define the future airport footprint. Geometry is set before land exists. Dredgers pull sand and soil from the ocean floor. Material flows continuously through pipelines. The sea begins to change.
Extracted material is released into containment zones. Sediment settles slowly underwater. Land formation begins invisibly.
Water clouds form briefly as sediment spreads. Currents are carefully managed. Precision controls nature. Floating guides mark the future seawall line. Accuracy here defines the island shape. Boundaries are locked.
Heavy equipment lowers stone layers to the seabed. Each layer stabilizes the next. The island edge is born.
Massive stones are placed along the perimeter. They absorb wave energy. Protection comes before height.
Reclaimed land grows in horizontal layers. Each layer settles before the next arrives. Stability is built slowly. Markers track vertical movement of the new land. Natural compression begins immediately. Engineering anticipates sinking. Extra material is added to account for future settlement. Final elevation is planned in advance. Precision offsets gravity. Temporary drainage paths appear across the land. Water is guided away deliberately. Moisture control begins early. Large rollers compact the surface repeatedly. Soil density increases with each pass. Strength replaces softness. Deep layers continue settling beneath the surface. Time and pressure work together. The island matures silently.
The seawall is observed along its full length. Alignment remains consistent. Protection is confirmed. From above, the artificial island shape is clear. Straight edges and long curves define it. The airport has a footprint.
Last major material deliveries are completed. Surface height reaches target levels. Land creation concludes.
Construction activity slows intentionally. The ground is allowed to settle further. Patience protects the future.
The artificial island stands complete, flat, stable, and contained. Vertical construction comes next. Uniformity improves stability. Vertical drains are installed deep into reclaimed soil. They accelerate water escape. Settlement becomes predictable. Drain installation repeats across the island grid. Spacing follows engineering models. Consistency controls behavior. Additional fill is placed temporarily above target elevation. Extra weight accelerates compression. Future sinking is reduced now. Preload material spreads evenly across large zones. Surface remains level despite added mass. Pressure works quietly.
Markers track settlement rates continuously. Compression follows expected curves. Adjustments remain minimal.
Construction pauses intentionally. Time allows deep layers to consolidate. Patience protects long-term performance. Temporary fill is removed gradually. Target elevations reappear. The ground is stronger than before.
Precise grids mark future terminal and runway zones. Coordinates align with master layout. Accuracy returns to the surface.
Test piles are driven into deep layers. Resistance is measured carefully. Foundation behavior is confirmed. Loads are applied to test piles incrementally. Movement remains within limits. Design assumptions are validated.
Production piles are driven across key zones. Vibration is controlled. Depth brings reliability. Piles are installed in clusters. Group behavior distributes loads evenly. Foundations gain redundancy.
Pile heads are trimmed to precise heights. Uniform tops prepare for caps. Precision remains visible.
Steel reinforcement fills the formwork. Spacing follows engineered patterns. Strength is shaped. Concrete fills in pile cap forms steadily. Surfaces level naturally. The foundation locks in.
Fresh concrete is protected from heat and moisture loss. Curing proceeds evenly. Durability is secured. Pile caps connect through ground beams. Loads transfer smoothly between supports. The system reads as one.
Foundation work concentrates under future terminal areas. Pile density increases where loads will be highest. The airport core takes shape.
Post-foundation settlement is measured again. Movement remains within tolerance. Confidence grows. Drainage layers are placed beneath pavements. Water paths are defined early. Longevity improves.
Perimeter seawall interfaces are checked near foundations. No differential movement appears. Boundaries remain stable.
Foundations across key zones reach completion. Equipment repositions for vertical work. Momentum shifts upward.
The alignment and levels here meet the targets perfectly.
I agree. The base is confirmed.
Ground improvement and deep foundations conclude. The island is structurally prepared. Terminal construction comes next.
They're making rapid progress on the vertical structure.
Yes, the scale is changing quickly now. We need to update the logistics plan.
Base connections are secured methodically. Verticality is checked and confirmed. Stability is established early. Horizontal beams connect the column rows. Spans stretch across wide terminal bays. Open interior space is preserved. Secondary members fill the grid between primary spans. Loads distribute evenly across the frame. The system stiffens. Metal decking is laid across steel frames. Surfaces prepare for concrete topping. The terminal gains solid planes. Concrete is poured over decking in stages. Vibration remains controlled. Floors cure evenly. With lifting paused, the frame stands still. Deflection remains within limits. Confidence builds.
Okay, cranes 1 and 2, synchronize the tension. Initiate the lift on my mark. Up slowly. Take it up slow. Bring it left just a fraction. All right, hold steady and set it down easy.
Okay, swing it in slowly. Watch the alignment. Coming down steady. Looks good. Hold it right there.
Parallel work begins on runway and taxiway zones. Base layers are graded precisely. Scale expands beyond the terminal.
Structural zones for services are framed within the terminal. Routes remain hidden from public areas. Function integrates early.
Expansion joints are installed across long spans. They allow controlled movement. Durability is protected.
The alignment on Sector 3 looks perfect. It matches the digital overlay exactly. We are cleared to proceed.
Roof decking is placed over trusses. Surfaces prepare for enclosure layers. Protection comes next.
Final pavement layers smooth the runway surface. Texture meets aircraft requirements. The airfield takes form. The main terminal superstructure stands complete. Interior space reads clearly. Enclosure and systems follow. Structural work slows as enclosure planning begins. Facade and roof systems approach. The next phase is set.
With the structure complete, attention shifts to enclosure. Edges of the terminal prepare for skin and roof layers.
Secondary framing is fixed along the terminal perimeter. Attachment points align with long spans. The envelope takes shape.
Large facade panels are lifted into position. Connections remain precise and concealed. The terminal begins to close. Seals and gaskets are installed between panels. Wind and moisture paths are controlled. Durability is built in.
All right, bring it down slow. Easy now, guide it into place.
Strong coastal winds pass over the roof surface. Panels remain stable. Design meets environment. Roof drainage elements are installed discreetly. Water paths are defined clearly. Maintenance is simplified.
Remaining roof panels close open gaps. The terminal is now sheltered. Interior work accelerates.
With lifting paused, the enclosed terminal stands still. No visible deflection appears. Confidence increases.
Interior walls and partitions begin to form. Zones for processing and circulation are defined. Function shapes space. Large mechanical ducts are routed above ceilings. Airflow paths remain direct. Efficiency guides layout.
Primary electrical routes are installed throughout the terminal. Capacity supports airport-scale demand. Systems remain hidden.
Plumbing lines run beneath floors and behind walls. Connections remain accessible. Reliability is prioritized.
Fire detection and suppression systems are installed. Coverage spans all zones. Safety integrates seamlessly.
Interior floors receive leveling layers. Surfaces are prepared for final finishes. Movement paths remain smooth. Lighting fixtures are installed within ceilings. Illumination spreads evenly. Wayfinding becomes intuitive. Check-in, security, and processing zones take shape. Clear spans support flexible layouts. Operations are anticipated. Back-of-house corridors form behind public areas. Staff movement remains separate. Efficiency improves. Wall finishes and durable surfaces are applied. Materials suit high-traffic use. Longevity guides selection. Mechanical, electrical, and structural systems are reviewed together. No conflicts appear. Integration is complete.
The terminal is fully enclosed and sealed. Interior conditions stabilize. Construction enters its final stage.
With active installation paused, interiors appear calm. Scale and flow become apparent. Completion feels close.
Bridges and interfaces toward airside areas are finalized. Movement between zones is smooth. The airport functions as one system. Facade and roof are observed as a complete system. Alignment and finish meet targets. Protection is confirmed.
Temporary platforms and materials are removed. Spaces clear for final testing. Order returns. The terminal stands enclosed and fully built out. Systems are installed but inactive. Testing approaches. Construction activity fades from view. Operational preparation begins. The end phase starts. Enclosure and interior construction conclude. The airport is structurally complete. Final validation comes next. All installed systems remain inactive and aligned. The terminal appears calm and ordered. Testing is about to begin.
Primary electrical systems activate gradually. Loads stabilize across networks. Capacity meets demand.
Detection and suppression systems are tested zone by zone. Signals respond immediately. Safety readiness is confirmed. Runway and taxiway systems are inspected. Surface performance meets aircraft requirements. Airfield readiness increases.
Wind and moisture move across the island. Structures remain unaffected. Design meets environment.
Vertical movement sensors are reviewed again. Settlement continues within predicted limits. Long-term behavior remains controlled.
Mechanical, electrical, and operational systems run together. No conflicts appear. The airport functions as one system. Limited operational activities begin inside the terminal. Movement remains smooth and quiet. Processes hold.
Timing synchronization is now optimal. Readiness level improved. Good work, team.
Aircraft taxi operations occur on completed pavements. Surface response remains stable. Scale becomes real.
The airport operates across all zones. Terminal and airfield perform together. Flow remains steady.
Passenger circulation is observed closely. Wide halls absorb volume comfortably. Design intent is confirmed.
After activity, systems return to rest. Cleanup proceeds efficiently. Order is restored.
Inspection routes allow easy access to systems. Monitoring remains continuous. Care is built in. Repeated operation shows consistent behavior. Settlement, structure, and systems remain stable. Reliability is proven.
The airport functions as part of regional transport. Sea, air, and
perimeter seawalls and foundations remain steady. No differential movement appears. The island holds.
Kansai International Airport stands fully operational. Engineering, precision, and patience converge.